point. If you would recall, we've been talking about finding and classifying critical points. And one of the things that I brought up was that we could use sometimes the second derivative to classify a critical point. Not always, but sometimes we can. So recall, we find critical points by finding points where the first derivative is 0 or undefined. That hasn't come up because we've been working mostly with polynomials. But critical points are when the first derivative is 0 or undefined. So we start by finding critical points, looking for points where the first derivative is equal to 0 or the first derivative is undefined. The undefined case hasn't come up yet because we've been dealing with polynomials. Our job is to classify the critical points as a local maximum, a local minimum, or neither of those. This is parentheses. So once we have found the critical points, our task will then be to classify each critical point as a local maximum, a local minimum, or neither a local maximum nor a local minimum. So the local maximum means the function is changing from increasing to decreasing. So the local max or local min is where the function is changing direction. A local maximum means f changes from increasing to decreasing. A local minimum means the function is changing from decreasing to increasing. One way we can do this is, since we're looking for a change in direction of the function, we could look for changes in sign of the first derivative. So if f is changing direction, that means f prime is changing sign. So f prime, if f is going from increasing to decreasing, we're looking for f prime to go from positive to negative. At a local maximum. At a local minimum, it'll just be the opposite. The function is changing from decreasing to increasing. So the first derivative will be changing from negative to positive. And that's one way we can classify our critical points. If we're going to declare that a critical point is neither a maximum nor a minimum, that means f is not changing direction. And that means the first derivative is not changing sign. to this, we want to add the second derivative, because sometimes the second derivative may have something to contribute in terms of our critical points. Oh, this is specifically for classifying critical points. Remember that the second derivative tells us about the concavity of a function. The second derivative tells us about the concavity of a function. So if the second derivative is positive at a point, then the function is concave up at that point. If the second derivative is negative at a point, then the function is concave down at that point. And what we can do is apply this to critical points. So if f is changing from increasing to decreasing, so if a function is changing from increasing to decreasing, then we should be drawing a function that is concave down. So at this point, we have a local maximum. As the function changes from increasing to decreasing. The first derivative changing from positive to negative. And we'll notice that the function is concave down at this point. So at this critical point, the function is concave down. And so the second derivative is going to be negative, indicating that the function is concave down. So if f is concave down, then f double prime is negative. So at a critical point, if the second derivative is negative, then we can conclude there's a local maximum. Because if we draw a function that is concave down at a critical point, then we must be drawing a local maximum. Here's a local minimum where our function is changing from decreasing to increasing. And notice that at this point, at this local minimum, f is concave up. So at that point, where the function is concave up, the second derivative will be positive. Any questions? So note that I have left some second derivative information off of the table at this point. At a critical point, if the second derivative is positive, then the function is concave up and we can conclude there's a local minimum. If at a critical point, the second derivative is negative, we can conclude that the function is concave down, so the function must be at a local maximum. But I have left out a case. What case is left out of the second derivative after these two? What's left? Isn't everything positive or negative? 0. I've left off what happens if the second derivative is equal to 0. This is because the second derivative equals 0 at a critical point tells us nothing. We get no conclusion. This does not mean we say no conclusion. It just means that the second derivative is not telling us anything. So it could be that we have a critical point that is neither a local maximum nor a local minimum. The function just goes flat, and in this case, just continues to increase. So we have neither. The function is increasing. No, that is not what I said. I said if f double prime is equal to 0 at a critical point, then we don't know. We don't get to say it's neither. That's making a conclusion. The second derivative test is providing no conclusion. So here's a case where f double prime is equal to 0. At this point, it's neither. And we should also point out that at this point, the function is changing concavity. So we would call this point an inflection point. So when a function is changing concavity, we refer to that as an inflection point. In this case, the second derivative was equal to 0 at a critical point, and it turned out to neither be a minimum nor a maximum, but it is also possible that we get a critical point we get a local max because our function is changing from increasing to decreasing. It's possible that the second derivative be equal to 0 at a critical point. If we have a local maximum and it just happens to be very flat, it's possible to have a local maximum and the second derivative be equal to 0. Note that the function is concave down going into this point and also concave down coming out of this point, so it is not an inflection point. So it's concave down and then concave down, so it's not an inflection point. This one would show as a critical point, but not an inflection point. This raises an important question. What are you talking about with this extra flat business? You might be looking at this descriptor, extra flat, and think that sounds like marketing, Leach. That doesn't sound like a real term. That's because that's marketing. It's not a real term. It's extra flat. It just means more derivatives are equal to 0. And so that means extra flat. Not only is the function flat, but the first derivative is also flat. And maybe even more derivatives are flat. Here's our favorite example of second derivative is 0, inflection point, second derivative is 0, not inflection point. We think of the function x to the 4th. This function is just extra flat at 0. F prime is 4x to the 3rd, and f double prime is 12x squared. F prime of 0 is equal to 0. F double prime of 0 is also equal to 0. There's a critical point at x equals 0. We think about what the graph of x to the 4th looks like. It's like a parabola with steeper sides and a flatter area around the vertex. So we know it's a local minimum just based on the graph. We also know it's a local minimum because the first derivative is negative when x is negative, and the first derivative is positive when x is positive. Both what we know about the graph of the function and the sign of the first derivative tells us that we have a local minimum at 0. The second derivative does not tell us anything about that critical point, because the second derivative is also equal to 0 at 0. But we notice that the second derivative is an x squared. So when x is negative, the second derivative is positive, so it's concave up. When x is positive, the second derivative is positive, so it's still concave up. So no matter what x is, as long as x is not 0, we get concave up. And we knew that just thinking about the graph. It is not an inflection point at 0 because we're not changing concavity. So it's not an inflection point. The function is not changing concavity. What's going on is that this function is just extra flat at 0. Any questions? Yes. F double prime tells us where the possible inflection points are. So when the second derivative is equal to 0, that's where the function might have an inflection point. Because when we're dealing with continuous functions, we're looking for, where inflection points are where the function changes concavity. So we're looking for places where the second derivative is changing sign, going from negative to positive or from positive to negative. When you're dealing with continuous functions, that's looking for places where the second derivative is equal to 0. Because it might be positive on one side and negative on the other. That means an inflection point. But it could be that we have the second derivative equal to 0 and it's not an inflection point, like in this case. It's really unfortunate the way we built the language around this. If the first derivative is equal to 0, that's definitely a critical point. If the second derivative is equal to 0, that might be an inflection point. Every time I come across this chapter, I'm like, oh, that's really annoying. But critical points can be classified as a maximum or a minimum. So there's an extra step. So the first derivative equals 0 is maybe a maximum or a minimum. The second derivative equals 0 is maybe an inflection point. Was everybody okay? The other version of this is just an x cubed. The first derivative is 3x squared. Now, what we know about x cubed is that we do not have a maximum or minimum. X cubed just goes flat but keeps increasing on both sides. That's indicated by the even power of its derivative. The first derivative is 3x squared. So the derivative is positive when x is negative and positive when x is positive. It's just 0 when x is 0. We have a critical point at 0. But it's neither a max nor a min. We know that by the graph of the function, because x cubed increases to 0 and then continues to increase. We know that by the first derivative. The first derivative is positive before 0 and positive after 0, telling us the function is increasing and then increasing. The second derivative is not telling us anything because the second derivative is equal to 0 again. In this case, we do have an inflection point at 0. Because the function changes concavity at 0. Before 0, we have concave down. After 0, we have concave up. So the function is changing concavity at 0. We can see that by looking at the graph, even though concavity is sometimes hard to read. But we can also see it by the second derivative. Before 0, 6x is going to be negative. When x is negative, 6x is negative. When x is positive, 6x is positive. So The second derivative is changing sign at x equals 0. So the function is changing concavity at x equals 0. Any questions? So an inflection point is a place where the concavity is changing. It's where the first derivative is changing direction. Oops. At an inflection point, the function will be changing concavity. That means at an inflection point, the second derivative will be changing sign. The one in the middle, first derivative, that has all that information about the direction and the concavity of the function. If the function is changing concavity and the second derivative is changing sign, in the middle, we've got sign, concavity. The middle one is direction. That means the first derivative is changing direction. Any questions? This is relevant to recent events. Because for a long time, the number of cases of COVID was increasing at an increasing rate. Then at a certain point, we reach an inflection point where cases are still increasing, but the rate at which they are increasing is slowing down. The first derivative has changed direction. So notice all through this graph, the function is increasing. After the inflection point, we are still increasing, but the amount of increase is decreasing. The direction of the first derivative is changed. Before the inflection point, the function is increasing and concave up. after the inflection point, the function is still increasing, but now is concave down. Before the inflection point, the first derivative was increasing, and after the inflection point, the first derivative is decreasing. We start off with the slope close to zero, then the slope reaches this high point, and then the slope starts to decrease. I should be more specific. In both cases, we would say that f prime is positive So that's what we mean with by an inflection point. The first derivative is changing direction. The function has changed concavity. The second derivative is changing sign. Any questions? Yes. Now this will be the graph of f. So if this is the graph y equals f of x. It represents an amount that is growing in the beginning. Then the amount of growth is slowing down, but it's still growing. F on both sides, F is increasing. On the left, F is increasing and concave up. On the right, F is increasing and concave down. On the left, F prime is positive and increasing. On the right, F prime is positive and decreasing. On the left, F double prime is positive. On the right, F double prime is negative. Any questions? Okay. So the second derivative can sometimes help us classify critical points. But if the second derivative is zero at a critical point, then we don't get to make a conclusion. We have to do something else. That's an important distinction. That comes up a lot in math. 2 semesters from now, when you're in Calc 3 and you're learning how to optimize functions, you're going to be doing the same things. You're going to be looking at first derivative, set equal to 0 and solve. Then you're going to look at some second derivatives. And if the second derivative delivers a 0, then you don't get to make a conclusion. You have to go back and do something else. At the end of Calc 2, when you're studying sequences, series, and power series, you're going to learn about the ratio test. And if the ratio test, the limit from the ratio test is greater than 1, then you can conclude diverges. If the limit from the ratio test is less than 1, you can conclude converges. If the limit from the ratio test is equal to 0, then you don't get to conclude anything based on the ratio test. That means you have to go do something else. You don't just get to say no conclusion. Any questions? Yes. Say that again. No, you have to do something else. Yeah, because if your second derivative test comes back 0 here, and you write neither maximum nor minimum, then if you say because the second derivative is equal to 0, it's neither a maximum nor minimum, you're still wrong. Because the second derivative didn't tell you that. The fact that the function changed, didn't change sign is what's telling you. Over on this previous one, if you look at this one and say it's a local minimum, or here, if you look at the second derivative and say it's 0, you would say it's neither local minimum nor local maximum, and you would be wrong because it's a local minimum. So when the second derivative is 0 at a critical point, you have to go do something else. Any questions? This raises the question, why would we want to look at the second derivative test if it won't always work? Sometimes if it's easy to find the second derivative test, it will be super obvious if the second derivative is going to be positive or negative at a given point. In these cases, I handpicked these cases. H of x had this same quality from 2 days ago. H of x fit this category. The thing that was giving you the 0, the critical point, was just extra flat at x plus 1. So if you remember the first derivative of h of x was just x plus 1 cubed. Well, 4 times x plus 1. 4 times the cube of the sum of x and 1. Any questions? It was just extra flat. So if the second derivative is negative at a critical point, then you can conclude the function is concave down, and so you have a local maximum. If the second derivative is positive at a critical point, then you can conclude that the function is concave up at the critical point, and so it must be a local minimum. If the second derivative is equal to 0, you're going to have to look at the first derivative to determine if the function is changing direction. Is everybody okay? Right. Remember, the point is knowing things, not classifying critical points. It's knowing how things are related. And so it's important to still go over this fact. When the second derivative is 0 at a critical point, then you get nothing. Good day, sir. Has anybody even seen Willy Wonka? Like the original one with Gene Wilder? That's the one where Gene Wilder has the purple hat on, and he's like leaning against his hand. It's like, oh, tell me more about, and then whatever. Or he's like, oh, you get nothing. Good day, sir. That's what he says when the second derivative is equal to 0. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.
Have a nice day.